All right. Thanks everybody for joining. I'm actually hoping before we get into this, curious to hear why everybody decided to come to the PJRT talk. Just here to learn is a fine answer, but I'm just curious if anybody's interested in building a plugin or maintaining one actively. So maybe go around the outside here.
Oh, I'm just interested to understand this API and how it's used.
Cool.
I'm just interested. No, I'd like to learn how to make a plugin to target, new silicon.
Yeah, cool.
We have our own fully custom thing, but trying to see if we try to use PJRT, then what would be the advantages and downsides? What's the limit of what we can do with it compared to fully custom solution?
And which company are you from?
Tesla.
Yes. Okay, very cool.
What platform or what framework are you targeting?
Mostly PyTorch and JAX as well.
Yeah, don't have to. I won't be offended.
For me, it's just trying to understand how it works.
We're building a custom AI compiler, so we just want to see if customers use OpenXLA, what those workflows look like for them.
Very cool. And which company are you?
Lemurian Labs.
Yes. Okay, we spoke at PyTorch conference.
So yeah, we indeed have a plugin. So in order to support that plugin, I want to understand more.
Great.
Yeah, just curious to learn.
Cool. So Sky over here is our PJRT expert, one of the original authors here. So for the more complicated or deeper questions, I'll be deferring to her, but this is more targeting at getting started on building a plugin, understanding how a framework interacts with it. Towards the end, I'll go into some code here. I built a plugin that just targets the StableHLO Reference Interpreter. So a basic, very little dependency on XLA stack, easy scaffolding code for third-party Accelerator to plug into. And as I was sort of dogfooding our own documentation, I took note of where I thought the difficult parts were and hoping to clear some of that up today. All right, so agenda. We'll talk about PJRT, the what and the why it exists, what the API looks like. We'll take a look inside of a plugin. So hopefully that would help with sort of visualizing the anatomy of what a plugin or building a plugin would look like, how different components would interact. And then we'll talk about how a typical interaction between a framework implementing PJRT APIs looks like, as well as what APIs on the plugin side typically get called. And then talking about existing documentation for building and testing your own plugin, existing tooling for testing it. And then lastly, we can dig through some code and look at the StableHLO Reference Interpreter plugin, which is just a very basic MLIR-based plugin, which I think probably tends to mimic a lot of what third-party accelerators are looking for. Something that takes StableHLO, bridges it to your IR, and then compiles, and that's sort of how you build your plugin. All right, so first off, the why does PJRT exist? As the number of frameworks increases, and so does the number of hardware, if we turn this into a problem of for each framework, you need to have some specific hardware knowledge, or for each hardware, you need to have some specific framework knowledge, it becomes an absolute maintenance nightmare. And so enter PJRT. It is a uniform API. The goal of PJRT is to sort of, or really the goal of OpenXLA as a whole, is to provide a buffer between the framework side and the hardware side. It allows both sides of that to innovate independently. If you are a hardware plugin, you can just worry about the StableHLO side, the passes that exist, build from there. Anytime a new framework pops up, and they have occasionally done so, you automatically get support for that thing. I'm going to come back to start with this one, actually. So just some links. We'll share these slides. These are things I was able to easily find online of existing frameworks that implement the PJRT side of things, as well as existing hardware that implements it. Some of this is open source, not all of it is, but for the open source projects, these are all links to GitHub or directly to code files, hoping that if you are looking into building your own PJRT plugin or enhance your existing one, these could be some code pointers. But even from this list alone, the second from the bottom one, ZML there, this was a Zig-based machine learning framework that popped up in the last month or two. And right on day one, they had support for every single hardware plugin right out of the box. Also, feel free to stop with questions at any time. Plenty of time for this talk. So what does PJRT communication look like? So there's two different places that you can plug into PJRT. We have a CAPI, which is stable, has backward compatibility guarantees to it. And then we have a C++ API, which has some, I guess, more object-oriented syntactic sugar to it. And that just wraps the CAPI. The C++ API has ties to XLA, so if you're thinking of plugging in with more of the XLA components, that can be a good place to get started. That's where a lot of our existing first-party plugins for GPU, XLA CPU are built, but the CAPI itself is a header-only dependency, very easy to pull into third-party projects without having a full XLA dependency.
If you implement the CAPI, does it provide full functionality, meaning the C++ API just wraps on top of it? Or there are some features that are only possible if you plug in Atlas C++?
Everything is the first one, the
First one,
CAPI.
okay.
It is confusing. The C++ API is a bigger API because it's actually used for other things at Google besides like plugging into JAX and PyTorch, XLA, and TensorFlow. But you don't need to implement those functions because they're not actually needed by the frameworks.
Okay.
So yeah, that's a confusing thing that maybe we need to document better. That like the C API is sort of the source of truth for what the frameworks actually need, because they do go through the C API always.
Right.
But yeah, the C++ API might be easier to implement or something.
So yeah, I mentioned there's different ways that you can integrate, either CAPI level, C++ API level. We categorize our integrations into 3 separate categories here. 2 of them are PJRT based, namely the full integration on the left here. This is, I like to phrase it as if you want XLA to be your compiler, if you intend for it to be doing the interesting bits of things, latency hiding, scheduling, bufferization, things like that, and you want to use the lower level XLO or XLA HLO based passes and machinery, that's where a full integration is useful. And there's also the light integration, which is more so, I have a compiler, I just want the framework support that OpenXLA provides. And so that's where you would plug in more at the StableHLO level, use all the hardware independent machinery that we have. We are actually actively working to make this light integration layer as useful as possible by taking some of the more useful hardware independent bits of the XLA full integration and pushing them towards the StableHLO level, so that more people can leverage them and get benefits from them, contribute to them as well. We always love that. And then the last is the export integration, which is a typical workflow of, I have my model on one machine and I want to serve it on another machine, be that a model server or your hardware is somewhere else. This is you need to package it up and send it somewhere, useful for edge things or for model servers. And that is, the current 2 ways that we package things are TF Lite and Save Model. There's also just raw StableHLO bytecode, which plenty of people have had success sending. That is a fully forward and backward compatible format. And we are looking into other model formats that don't have any TensorFlow dependency. I think that there's a subtle goal for the next year to have a better archive format that we can actually declare a part of OpenXLA. All right, so let's take a look inside of a PJRT plugin. The highest level thing is the PJRT client. And this is all interaction between a framework and a plugin goes through the PJRT client. So some things about it is, inside of a client, there are devices, memory spaces, and buffers. The client itself tends to own all of the devices and all the memory spaces. So once you are cleaning up a client, that's when those things will be released. Buffers themselves tend to be owned by the memory spaces there. This is all fairly more on the conceptual side. This is just how our C++ plugins look. If you're implementing the CAPI, you don't necessarily need this hierarchy. It's just, if you're looking through existing code, this is the structure that we have built existing plugins on top of. And yeah, memory spaces can have or devices can have multiple memory spaces. Maybe one of them is a global shared one of them spin to the device. And memory spaces can be shared by multiple devices as well, especially if they're global or located more on the CPU side of things. So just covering a few of the responsibilities of a plugin. When I was implementing the reference interpreter plugin, one of the things that I thought was the most difficult was there are, as Sky mentioned, a whole lot of methods and you don't need to implement all of them. So it's not exactly trivial to figure out which ones are fully required. But at its core, the responsibilities of PJRT client are device queries, what devices are available, which ones can I send computations to now. Memory management, I'm the framework, I want to pass you some data. You can store it either on a device, figure out where to put it. Compilation, here's a StableHLO program, return me back something that when I have input arguments, you can execute it and give me a result. Execution, of course, is I have that executable. Here's some input arguments, give me a result. And then there's some other bookkeeping. There's some like sort of advanced topics of if memory is, or if a buffer is located in a shared location, we can access it without copying it back to the host. And then there's some things you can do there. We'll talk more about we'll talk more about all of these in the next few slides. All right, so a typical framework and plugin interaction. The way I went about doing this is by putting a trace on every single method that I implemented, running some tests on JAX, and then looking at the logs, and then just sort of zooming out a little bit and giving a higher level look as to how a framework and plugin interaction goes. So first step is, well, once the framework creates your plugin, it wants to know like what is available on this plugin, what devices do you have? And so there's an API called devices. The client will report back to the framework and say, I have 2 devices. Here's their IDs. They have a bit more information than that. But at its core, it's just reporting back to the framework what its capabilities are. The next thing it does is, as the framework is tracing a compilation and generating StableHLO, or tracing a program and generating StableHLO, it says, here's a module. I need you to compile this module and give me back something that when we have that input argument data, we can execute. But as it started with the compilation and forming the executable. And the thing that comes back here is a PJRT loaded executable. And this is, again, everything needed for execution except for input arguments. One thing we've recently added, probably should have had a slide for it as well, is right before compilation, the framework can query what version of StableHLO is the PJRT plugin using. And what you can do with that is give very precise forward compatibility. The client, this is done using PJRT attributes. And if you have an attribute, we'll look through this in the code, called StableHLO current version. It will report back to the framework. The framework will say, okay, cool, your version is 1.7. I'm at 1.9. I'll downgrade it 2 versions and then ship the computation there. The benefit of that precise communication is if you have a new feature in StableHLO and it was just rolled out a week ago, as soon as you cut a new release of your plugin, you can use that feature immediately. And this was just an upgrade from time boxing it and saying 12 weeks of compatibility, wait 12 weeks for all new features. And then next, now we have our executable ready, but we need some data to run on it. The API for this one is buffer from host buffer. It takes an XLA literal and says, here's some data and the device which we're going to be executing on. Store this data somewhere where that device can access it, be that pinned to the device or in some global shared memory space. And then it returns pointers to all of those buffers that are owned, again, by the PJRT client. And now we have, let's run this thing. We have an executable, we have our buffers. The arguments that get passed back in to your execute function are the same buffers that are owned by the device. That was one thing that had confused me when I was initially implementing this thing, is we have input arguments. Where are they coming from? Do I need to copy them? But the way that the framework interaction works is it first says, here's the data. You store it somewhere where you can run it on this device. So when it comes back in, everything will be in the right place. And the result there is you create new buffers. They're still located on the PJRT, inside of the PJRT client and owned by the PJRT client. Those are the results, and they report it back to the PJRT framework. There's some optimizations that you can do here. What we're in this sense, we're talking about more synchronous execution here, where the framework was waiting for the results and it came back. But there are certainly ways to do this asynchronously, and I have a slide on that later. And then now we're at the point where we have our results, and the framework itself wants to actually start working with the data that's stored inside these buffers. So if there's a method called is on CPU. If that one returns true, there's a minor optimization that says if it's on CPU, it's in a shared memory space, I can access that without copying it. And it calls this method called getExternal reference, which just says this variable X inside of the framework side of things might live longer than the rest of that, or might live longer than the rest of the plugin itself. And so we need to just make sure that the lifetime of this buffer is managed by the framework. And so that's what external references purpose is. If it's not located on CPU, yes.
Yeah, one quick question. Are the framework and PGR client in the same process memory or yeah, not?
Yeah, so it's like, yes,
Oh, yes.
but then like usually PJRT, if you're running on, if it's like an accelerator platform, then all the memory that we're talking about is device memory. So then it's like the process doesn't really matter. It's like the host can't directly access that device memory except through the PJRT interface. And if the PJRT plugin is actually managing host memory because it's like, you know, a CPU device instead of like some external accelerator over PCIe, that's when this comes into play, because then now, yeah, like the host and the plugin are like literally accessing the same memory, and then so we have APIs to manage the sharing. Yeah, but usually like the kind of like, yeah, if you have like an external, like, you know, a GPU, then you don't need this because you can't share the memory between the host and the device that way anyway.
Yeah. Thank you.
And yeah, in those cases where you are using a GPU and it's not in some shared memory space that you can access, the method there is called toLiteral, and all it does is it says, take this buffer, doesn't matter what format you have the data inside the buffer, you know how to copy it back to that XLA literal format. And then that's what the frameworks operate on. And so, yeah, then in this case, we were talking about it is CPU case. The thing that comes back is an external reference with the void pointer to some underlying data. Going one step further on this external reference thread, some other APIs that might need to be needed if you are using this shared memory approach, is you need to tell the framework how to interpret that void pointer. So things like, what's the size in bytes, what's the shape, what's the type, and then that allows the framework to interpret that void star pointer of data. Cool. And so then, yeah, these would return things like it's 64 bytes of I32 scalars. And then last but not least is the cleanup. Once the framework is done using buffers, buffers all know how to delete themselves and mark themselves as deleted. And there are also queries for, is this thing deleted? So there needs to be some management of deletion state of buffers. And so then that's where the cleanup and releasing can happen inside of that plugin. Okay, and then the one last concept I wanted to cover, the plugin, the reference interpreter plugin that I implemented is synchronous. Once you call the execute method, you wait for execution to be done and then come back. However, there is this case where in the framework, you might be saying X equals some function, you do a whole bunch of things that don't require X, and then later on you print X. In those cases, you don't need to block on waiting for X there. There might be plenty of other computations that you could dispatch to other devices while this is all happening. And the way that we accomplish this in the PJRT world is futures. There are buffers and devices both know when they are in a ready state. And then the way it works for execution with futures is you call execute, the client just creates these uninitialized buffers that are not yet ready to be inspected, and then returns those back to the framework. So what the framework is getting back is this vector of uninitialized buffers that are not yet ready that you can query when they are ready or wait for them when they are ready. And it's not until we hit this print X line where you actually need to wait for that value of X to be ready there. And so, yeah, when we can get into the code and you see PJRT futures, this is largely what they are aiming to accomplish, is allowing execution to carry on without blocking on execution.
Yeah, and this is also really important. It's like how we get good performance, even though we're writing Python code, because like the Python thread is just enqueuing stuff to the runtime. And so hopefully it can run ahead of the actual execution. But yeah, you can always implement things synchronously to start because it's easier. It's just you might get more blocked on Python overheads.
I have a quick question. So the execute method itself, it can return a future, right, for when the execution has finished. Is that correct? Or is it only?
Yeah, the model is that like, yeah, all of these buffers are actually futures.
Right.
It's like a handle. And then it's like, yeah, JAX, and I'm guessing PyTorch XLA, like, you know, it like carefully hides this from the user. And anytime like they print or do something that actually like the value needs to be accessed directly from Python, will like secretly block and get the data. But
Right, so it's only on the buffer level.
yeah, because execute is async, compilation is actually sync, interestingly. So yeah, I think it's mainly the buffer transfers and the execution that's async.
Devices, maybe waiting for a device to become available.
That I think is also sync, like when you initialize.
okay.
Yeah, because that just happens once at the beginning. So yeah, it's mainly around like the execution and the buffer transfers. Like those can all just get queued up by Python, and then the runtime can work away at those.
But yeah, there's an explicit method on every buffer that is get something you can wait on for my buffer to become ready.
Yeah, so buffers like look synchronous, but they're not. And so when you're actually implementing a runtime, it's like it's not like you can implement it synchronously, but it's designed to be async.
Cool. And yeah, sort of as Sky mentioned, there's different levels of a plugin you could implement. There's many features that are technically optional, but you're probably going to want to implement if you want to reach peak performance with your plugin. Asynchronous computation is one of them. The plugin that I implemented is just single host, single device, doesn't manage communication, no send receive. Those are all things you can implement. There are dedicated APIs for all of those things. Sharding, custom layouts, smarter memory management, like JAX donating a buffer, or having buffers that are passed into your computation that can also be shared with the output. Plenty of things like that. Sky, I don't know if there's anything else you'd want to add to that. Yeah.
So one quick question. So for multi-host support, so do we need to have one PGR client for each device, even in one single host?
No,
No. Okay.
you
So-
can if you
Oh.
want.
But no-
JAX doesn't run that way though. I think PyTorch XLA might run that way.
Sure.
Yeah. But yeah, it definitely supports having one process per host. So that would be one client per host, but then each host has its own client.
Okay.
Yeah, and at least even in JAX, like, yeah, because that's just how like users run JAX code.
Okay.
You can like optional, like now it's like part of the contract with the user because it's like how many Python processes are they starting? Like JAX is going to start one client per process. But like there are ways you can run multiple processes per host if you want. Like people do this on GPU by using like the CUDA visible devices environment variable, and then you'll have like one Python process on one GPU and one on another GPU. And then in theory, yeah, I think if you call jax.distributed.initialize, like you can like tell those two clients about each other, then they act, it's like it doesn't matter if it's a multi-host or just multi-process on one host, like the PJRT clients interact the same way, like set up Nickel the same way. So, but yeah, the default for JAX is one process per host.
So even they are a card, maybe a GPU card in the same host, we still only need one client and to coordinate between those hosts.
Yeah. Yeah, and you can see in our implementations, like in the GPU implementation, it manages multiple devices, and when you call execute, it's actually like launching on all the devices.
Okay.
Yeah.
All right, so now talking about some of the resources we have for getting started building a plugin as well as for testing existing plugins. The PJRT integration markdown doc, actually I should also show on openxla.org, switching tab. We have much of this documentation is still work in progress to get this up to a much better place, but a lot of this presentation is distilled into documentation here as well, with some dedicated code pointers to various points of what we're talking about. The documentation referencing there is how to get started building your own plugin, and this walks through things like the basic getting started, as well as, okay, you've made your plugin, how do you build it in such a way that you can use it with JAX? How do you set up your directory structure that JAX can find it? Or PyTorch XLA, and confirm that this works for both. Yeah, a simple test case that you can run with your plugin on JAX. So we just wanted to point out that documentation. There are also linked in this presentation plenty of code pointers to existing plugins CPU, GPU, C API, C++ API. We'll go over briefly the StableHLO reference plugin. Yeah, and then just considerations back to the StableHLO reference plugin. One of the goals of this is to make an easy getting started point for starting your plugin for especially low XLA, mostly just want StableHLO as the input format, third-party accelerator plugins. And we will continue enhancing it in that direction. As I mentioned, now currently it's synchronous. Making it asynchronous is one of the first steps we're going to take. But the existing CPU and GPU plugins are both very mature with a whole lot of code for the copy buffer from here to here code is several hundred lines and not very easy to understand. So we wanted to try to keep this one a lower code, more focus on the concepts, easy starting point. Some things to consider if you are using this as your starting point is that everything's in global memory space. You're going to have to manage moving buffers from a framework into a memory space accessible by your device, which is more likely going to be some hardware pinned memory spaces, as well as its single device, single threaded futures, like as I mentioned, are going to be the next addition to this. And then two things I wanted to call out from the testing side of things. As I was building my plugin, I had the thought of, wouldn't it be great if we had some kind of a unit test infrastructure that just pretended to be a framework and served you hard-coded StableHLO blobs? Well, turns out that already existed, and I only found that when I was digging through some code, so I just wanted to signal boost it. The C API test factory acts like a framework, and it mostly focuses on like query APIs. Do you have devices? Can I interact with your devices? Can I send a buffer to one of your devices? It does not, as far as I know yet, and we'll probably be changing this, worry about compilation or execution to enforce correctness there. We have a different plugin called the Client Test Factory, Register Test Client Factory. And this one is sort of the next layer above the C API test, which also focuses on execution, checking your results, serving you StableHLO or HLO blobs of data, and then running computations and making sure that it all looks good. So yeah, just wanted to call out those two things, code pointers to each, both in these slides when they're posted. And then one other thing that I found useful as at least starting point for ensuring that your plugin is correct is the JAX LAX test suite. I started with the JAX Metal plugin test suite, which is this LAX Metal test.py. It's a subset of the full JAX LAX tests, and so it's a decent place to get started. But if you build your code, put things in the right place, and then you run PyTest, you will be running, I think this was something like 1,300 tests.
There's a lot of like sub test cases.
Yeah,
Like
it's
parameterized.
very parameterized, high coverage in terms of JAX primitives. And so yeah, as far as running small unit tests and figuring out what works and what doesn't, I found this super useful. Okay, and I guess before we start looking at some code, are there any questions on anything we've talked about?
So any good debugging tips? Maybe if we face any issue, how we debugging from your suggestion?
So because this is built as a shared object that gets loaded, stack traces were not always there or useful. I don't know if there's tips on that one. I think just good logging tended to be my best debugging thing, and we'll see as we're going through this code, there's heavily laced with log statements.
Yeah, I'm trying to think. I mean, a lot of it, I think, like kind of, it's like it's in your hands. Like you're building the plugin, and like usually it's like when you're building a plugin, you're debugging the plugin. So then it's like most of the logic is not in this interface. It's like literally what it's doing. It's in the implementation, right? Like that's the hard part. For things at the interface, I'm trying to think of like common bugs that.
I've noted some of them, like when I was, my hope with having scaffolding code to get started from is that the interesting and more bug-prone parts of building a plugin will be in the layer of storing buffers on your device or compiling for your device or things like that, in which case debugging comes down to how do you debug your existing hardware today. But when I was getting started building it, some things were like, if a computation had no results, it
Yeah.
would fail. And this was things that were just discovered by running those lax parameterized test suite.
I guess I would say I work on JAX, by the way, so I have a very JAX focused view of the world, but the JAX unit tests do offer good coverage. One thing to note is that it might be like too good because they are like, yeah, if you run like the full test suite, like all the files in there, you're exercising like all these features that maybe your use like aren't MVP for your users. This like kind of like those like optional advanced features. So I think running the lax unit test is a good idea.
That might be why starting with the metal test is good. It doesn't use many of those.
Yeah, I mean, it's not really a debugging tip, just like an FYI tip. If like tests are failing, it might like look at what the test is actually doing. It might be something you don't care about for your like initial thing.
Is there some overarching, like for example, tracing framework, right? Like you have all these API functions. Is there like some already built-in logging framework at that level before you get to the plugin side where you could just use that to generate
And I
a
asked
Chrome tracing
someone,
or something like that?
did we actually add it? Let me quickly check.
Yeah, I think
The
this type
reference.
of things would just help to understand the global workflow, right? Like you would see,
Yeah.
we've requested compilation. Okay, you return as a result compilation, or we requested a buffer and so on. I guess that could be something that can help.
It's all ABSIL logging as far as that goes, but the CPU plugin I think does a really good job at like making IDs for each thread that gets launched and making sure that traces are attached to the thread that they're on.
Yeah, we should add this. We don't have this. I thought we had. We should add to the C API client, which is like what JAX calls, and like eventually calls the plugin. We should just add a log for every single call in there. That like a vlog.
Okay.
That you can optionally turn on. That's a good idea, but we don't have it yet.
You should even do a like a trace style, right? Like how do you put it? Like whatever interface we use to generate the Chrome traces and this kind of stuff, because then you can see the boundaries of the
Oh,
API call as well, right?
Out of that.
Yeah.
Yeah, I know this
like-
type of interface end up super useful to debug high level.
Bring it down. Good idea. Yeah, because that is super useful. So I often add this logging by hand. Not
Yeah,
trace is a good idea. But
You can always do it when you implement your own API, right? You just
Yeah.
put it on all the calls. So it's not the end of the world.
yeah, but we could like put it on like the top layer that JAX calls, and then you kind of get it for free across all plugins.
There was some stuff on CPU and it might be doing this. I'm not sure. All right. Anyway, let's.
Just another quick question regarding this. So if you implement the C API, like there's a lot of memory management that's basically on you, and it's very easy to, mess up and have use after free bugs and all of that stuff. Is that usually caught by just using like Wallgrind or whatever usual tooling for detecting that, or?
I used like the Clang ASAN a lot. I haven't used Valgrind, but I imagine that also works. Yeah, but yes. Yeah, we can't catch or it can't catch like device memory bugs, but for like the actual working with the C API itself, then yeah, like ASAN saves my life a lot of times.
Cool. Okay, so just looking at the reference plugin briefly. I guess one design pattern that I've tended to like when writing PJRT plugins is hide everything in the C++ file. Basically enforce that the API surface of a plugin is exactly what the plugin of this base class that we're using is. So there's no trickery or hackery, or nobody can misuse your plugin. They can only use the APIs that we are saying are dedicated PJRT APIs. So here's the main PJRT reference client plugin. The hierarchy that we had shown with the client has devices, has memory spaces. It's all implemented inside of this class. You can see it's just initialized. You make devices. These are just unique pointers of owned devices as well as pair pointers. It owns the memory spaces, and then you attach memory spaces to the devices. So this is initializing the client involves setting up that picture of a class hierarchy that we had shown earlier, namely this one right here. This one, the compile method is the first one that we had talked about getting called. I think I put this all in the executable itself. As I mentioned, this is all MLIR based, so my MLIR based compile method just takes the MLIR module op. I think I decompose CHLO, which is the slightly higher level offset that can be decomposed into StableHLO. Decompose all of that, look for any custom calls so I can error here. This was another thing that got caught, is that sharding comes through as custom calls. You can, and I advise everybody who's making a third-party plugin, you can use any hardware-independent StableHLO optimization machinery. This is one area that we are really starting to enhance as we're removing the MHLO layer and pushing all the interesting stuff to StableHLO. Currently, we have this aggressive simplification past the API service, but this is likely going to change as we're getting forward and have to start building in some semblance of a cost model, I suppose. But I do advise all third-party plugins take advantage of hardware-independent machinery that exists in the OpenXLA system. And then, yeah, it just takes that module after you've optimized it and stores it for later. And then it returns a loaded executable, which has the module that's stored, has devices that it's able to access, and then knows its client because of pretty much this the entire diagram of devices, memory spaces also all has back pointers, so they all know who they're interacting with. The other ones I wanted to show are buffers, moving data buffer from host buffer. Oh, sorry, I guess it was just these ones. As a framework is transferring data to your plugin, it calls buffer from host buffer, which I have just dispatching to this, create some MLIR dense elements attribute from the XLA literal. I wanted to point out that we have in the XLA repo dedicated APIs for translating between MLIR dense elements attributes and XLA literals. We have APIs for both directions. So if you are building an MLIR based plugin and you need to get to this, we have APIs for those sorts of things. And then execute is the next one to show. And it's actually just in the execute function. There are a few different execute methods, and Sky, maybe you could talk about the nuance between them. My understanding is some of them will pass in just a list of argument handles. These ones are expected to operate on a single device. We have one computation to do. And then other ones will take in basically a vector of vectors of arguments. And these are ones that are spun off on multiple devices.
Do these all get called by the unit test?
By the unit test, no.
Okay, yeah, I haven't looked at this in a while. Like, if you look at the C API, there's only one execute call. The C++ API, that's like our real working day-to-day API and has a lot more historical stuff in it. So yeah, like if you look at the C API, we consolidated like all the options that are actually needed by the framework into options. And now I'll have to remember how they map back to all of these. We can literally look at the C++ wrapper implementation to definitively answer that question. But yeah, I don't think you need all of them. Like, I don't think you need execute portable.
I don't think you do. It's really just execute sharded was my experience.
I think like execute was the original API that like dispatched across all devices maybe, and then execute sharded executes across, it just executes on one device. This is a little confusing because the devices are actually baked into the executable. So like execute sharded is a little bit redundant. I forget why we needed it. I think maybe it was like some precursor to execute portable, which is not fully supported. And that's for like, we have like kind of some half-baked functionality to create a portable executable, which means you can launch it on different devices. You don't have to like bake in the devices that it's going to run on at compile time. So I don't like, I would be surprised if we really ever run into execute portable, because that's very,
I haven't encountered.
very working for us. But yeah, the model is sort of like, and this is kind of broken that like when you call compile, you're actually like baking in the devices that is going to run on. Even though like maybe if you were going to run on like a similar set of devices, you wouldn't need to recompile. So yeah, and maybe does it just call execute sharded?
That was the only one that I mean, I only ran the lax metal tests, but it seemed like that was the only one.
Okay, yeah. So maybe just an execute sharded.
Maybe once we're through with this, if you want to show off the C API towards the end.
Sure, yeah.
Okay, and then I guess the last two things to show here are added tracing to every single class in the base one, so it's easy to see exactly the order of where things are going. Easy to see what buffers are getting passed in when those methods are called, so hopefully that helps track down where issues there are. And then execute with reference interpreter is the sort of guts of execution here. As I had noted between the whole synchronous and asynchronous thing, this method here can absolutely just create a buffer, return a buffer, and queue the work, and then just the buffer needs to know when it's ready. So code some way of the buffer knowing when its computation has completed. But yeah, for this this method here, it's just converting things into dense elements attributes, making sure that everything's in the right MLIR module context, and then this is the StableHLO Reference Interpreter evaluation. If we were building this for a different plugin, it would be the compile method. Instead of storing a module, it would create the hardware is executable, be that some flat buffer or something else, bytecode itself. And then execute is in queuing the job. And as I noted, this one is fully synchronous, so buffers are always ready, and status, if we get down here, is always returning okay, because there is no such thing as a buffer that isn't ready in a synchronous world.
I just looked up the implementation, and the C API does support all three methods. So I think it like execute, portable, sharded, whatever. But I just don't think like normal Jax execution uses all of those, and I can't speak to PyTorch XLA. So yeah, I guess I would just put logging and see what it gets called. How we literally like went around, like when we were implementing the C API, we sort of started by just like returning an error or raising an error for every single method, and then implementing all the ones that were raised. So that's one tip for doing that.
Right. Okay, I think that's the end of things I wanted to show as far as the code go. I wanted to just give an idea of the structure of things where you could plug in if you wanted to modify or enhance it. Did you want to give a quick show of the C API at all?
Yeah, sure. Should I just present?
Hand you my laptop.
Oh yeah, that might be easier. Okay, so let's.
We'll be sharing that tab.
Yeah, I'm gonna go so I can use the computer. Yeah, so this is the main header file. There are some. We need to organize this better to have all the headers in one directory with nothing else. But there's some extensions as well. I'll just like really briefly kind of show the structure of all these functions. So yeah, the beginning is kind of wonky, but like if we go down, like let's look at execute. Okay, so just to give you a taste of what the C API looks like, because it looks kind of weird. All like actual endpoints of the API, like functions you need to implement, look like this. So they all take in an args struct and nothing else. This contains all the inputs and outputs of the function and input outputs. And then they all return error, which could be null if there's no error, everything was fine. And then it's also a type def. We'll get to that in a second. And then so, yeah, like I said, the arg structs usually come up right on top. And so this is all the inputs and all the outputs. We do this for ABI compatibility. Like we can add inputs and outputs to the end, and then you check the version or the struct size, depending on what side of the boundary you are on. And you can do something smart. So that's just kind of how to read these. And then, yeah, and so you can see like all those, you know, it's like this is the only execute method. And I think like execute device makes it the difference between like sharded, not sharded. And then I think we can like check on the executable itself, whether it's portable. And then, yeah, so I like the C API was made after the C++ API. Like the C++ API was just like originally how JAX like used XLA before we had any pluggability. So like, and I worked on the C API, so I'm biased. I find it like we sort of like cleaned some stuff up. So I actually find it to be like a more clear reference, just because, you know, it was our second try. And then the last thing I'll go over really briefly, just so you like know what the structure of this thing looks like. There are a lot of methods. Is that, yeah, so you'll notice that all these functions are not actually functions, they're type defs. We do this to avoid, we want, like, we don't want to create symbols for these functions, because if you want to load multiple plugins, then like the symbol, you don't want symbol collisions, you have to like DL-sim, it's hard if you have a million different functions. So what we do is wrap everything up into this one PJRT API struct. And so this is just like a little macro that basically like, yeah, like instantiates one of these type defs for each function. So this is like the actual entry point into the whole plugin. And if you look at the C++ implementations, we have some machinery for like automatically generating this. Or, you know, you have to like enter in all your like actual symbol names, but then it will put it all into the struct for you. This is also a good list of literally all the functions. And then we should document this in this header file. Basically, the contract is every plugin defines a symbol called get PJRT API or something. We should really write that at the bottom of this doc. It's not in the header file because like, yeah, we're like trying to avoid like, why did we not put it in the header file? There was some like obscure linking reason that I don't remember. But you make your own header file that has that one endpoint in it, and that thing returns one of these PJRT APIs that, you know, is populated with all the endpoints to your actual implementations of these functions. So from like the framework perspective, you like DL open the plugin.so, you DL sim get PJRT API, and you know, you can do that on many plugins and avoid simple collisions. And then that is the entry point to everything. So yeah, that's just like functionally, it's like basically the same as the C++ API. So the main differences are maybe it's a little cleaned up, and it has this kind of unusual structure for API compatibility and actually making the linking and DL opening possible.
We also have, or there exists, some scaffolding for getting started with the C API as well. I saw very recently that Tenstorrent had made a PJRT plugin, and if you look in here, it is just everything that Sky showed, but implementing some of those methods and then binding to the C API methods so that the struct itself can properly be populated. Yeah. Okay. A little time for questions or discussion. Are there any thoughts or questions?
I have one. When you have a multi-device model, so you have, let's say, or rather you have multiple cores of the same XPU, right? Is the general model to have like one instance of the plugin for each of them, or you have one managing the dispatch to the different cores?
Usually one plugin for, or like one instance of the plugin for all
the cores.
Yeah. You don't have that was kind of like what you were asking.
Yeah.
It's like you don't have to do it that way. But then because JAX starts one client per process, you'll have to like explain to your users you have to start multiple JAX processes, one per core. I could draw a picture.
JAX would start only one process of the Oh,
It's like JAX for each, like, we call it like backend or platform.
Yeah.
We'll just create one.
okay.
So if you have two JAX processes, then they'll like each have their own client, and then maybe each client is driving its own device. And then it kind of takes advantage of like, the multi-host machinery, which your plugin has to support. But it's like actually just multi-process machinery. I guess it's different between host and process because how you communicate, but like, yeah, that's up to your plugin. It's usually easier to implement one process with
Yeah.
all the devices because then you don't have to communicate between them.
Yeah, that's what that was going to be my follow-up question. If you were going the other way, like how do you manage communication between different devices potentially through non-DRAM memory and stuff?
Yeah. Okay.
But you put it, no, but if you put it in a single one, you're managing the memory on your side anyway. So, that's fine. And another question though is, do we, when you get a work request, right? Do you know potentially where the I/O comes from? Because there's this buffer management, but does PJRT assume that the buffers, the shared buffer basically live in DRAM? Or do I know where my output is going to go? For example, well, already ahead of time, when I'm asked about compilation, do I know, oh, this output is going to be used by that other device or that other device? So I can decide where it's supposed to go.
So by default, no. I think, yeah, I know more about like TPUs and GPUs. Okay, yeah, so like the kind of like default way, I'm gonna try to meet you in the middle because I like half understand what you're asking.
I think I could give an example. Like let's say you ask the TPU plugin for compilation, right? And you have an output.
Yeah.
But if you knew ahead of time that it's going to go to the GPU, depending on your platform, you could write to a specific. Yeah, you could have your buffer not in DRAM, in general DRAM, but you could directly write to GPU memory, for example.
So that's where like the memory spaces concept comes into
Okay.
play. And this is kind of like a new and advanced feature, like, because like the default way of running JAX is that like each device just has like its own local memory because we're doing
Yeah.
GPUs. It's like whatever the HBM or VRAM is. And then like, right, if you're running on one GPU and you're going to run something else on another GPU, then it's like, okay, it gets produced locally on this GPU's VRAM and you have to like device put it, like do a D to D transfer to the other GPU. But memory spaces, you can define, you could be like, if your runtime and plugin supports it, you can be like, okay, I'm going to run on this GPU, but like the user can optionally specify the memory space to be like this GPU's memory. And then it's like up to your execute call to make sure that it ends up there. So yeah, like you can model shared memory this way. It is still, at least in JAX, like because it's like, how do we know where it's going to go? So it's like the user APIs it's like the user tells you. Like when you run the compile call, you basically like the user is like, actually, this is the output memory space because I know I'm going to go do this. And that's also how we do, I think that's like part of how we model like certain types of host offload. Like, you might be like, actually, this output is just like host memory, which is shared among all devices, like give users that option. So yeah, I would look into like the memory spaces. Like I think basically you want to implement, like by default, like if you don't support this, it's like each device just has one memory space. Like users don't specify anything because there's only one choice. But like you can actually have each device have access to multiple memory spaces, which you somehow, I think you like set it up when you like initialize the device descriptions.
Do a static decision when you do. Okay.
Yeah, it's like we sort of have this like concept of a topology, which is like just a description of like the hardware and like how many devices are there and how many memory spaces are there and like what's the graph between the devices and the memory spaces. So you can set that up, and then that gives users the flexibility to be like, okay, I'm running on this device and I want it to be output on this memory space, and then like your compile and execute calls have to support that.
Okay.
Or you raise an error. So I think that's how you would do it. You would have multiple, like devices would have multiple memory spaces. And then users could optionally, like I think each device still has to have a default memory space, and then users can optionally override the default if there's others available. This is an advanced feature. So let us know if it doesn't work, if like the interface or JAX is not working correctly.
Anything else? Great. All right. I'm gonna pause the recording.